So last week we covered about the matrix norms and eigenvalues, and that was to lead up to what we're going to discuss this week and also next week. And so today we're in chapter 5 in the notes, and that's on stationary iterative methods. So that's what we're going to get through today. And so if we have...
It's chapter 4 in the textbook.
Chapter 4 was on direct method. Oh, I'm not sure in...
Okay,
Are you talking about in the textbook?
Yeah.
I'm not sure what it is in the other textbook. Okay, so if you're given a system of n linear equations and n unknowns, then this system can be described, of course, by solving the system AX equals B, where A is an n by n invertible matrix. So previously, before last week, actually before spring break, we looked at what we call direct methods for solving these types of systems, and Gaussian elimination, Cholesky, and all those are examples of direct methods. But in conjunction with forward and back substitution as well, we were able to find the solution to these types of systems. But there are a couple of drawbacks to direct methods, that type of approach. So that's what we're going to discuss to establish the need for what we're going to talk about today, which is the iterative methods. So first of all, if we have an approximation, to the solution X, direct methods do not provide any means of taking advantage of that information. So that's our first drawback. So if we had an approximation to the solution and we're using a direct method, then there's nothing that we can do to use the information that we already have, because we have to go through the whole process to find the solution. Secondly, of course, is if we only require an approximate solution. Direct methods are going to give you the exact solution because there are no intermediate solutions, of course, with round-off error or other types of error that are accumulated, but you can't just get an approximate solution. You have to go through the whole process to get your exact solution. So it's like I was saying, it's not possible to terminate the algorithm for a direct method to get such an approximation. So thirdly, as the matrix A is sparse, meaning that it has a lot of zeros, Gaussian elimination or other direct methods can cause what we call fill-in. So that's an introduction of non-zero elements to the matrix, and that reduces efficiency as well. So in particular, if we have large, sparse systems, that's really where we want to use these iterative methods. Okay. And then lastly, in some cases, we may not even have a matrix for A So A may not be represented as a two-dimensional array. Or a set of vectors. Maybe the only information that we have is that it's implicitly represented by a function. That returns as outputs the matrix vector product AX. Given X as the input. So direct method would not be practical because we don't have the entries of A readily available. So now that we've established a need for these iterative methods, well, these are the reasons that we look into these iterative methods. So in particular, an iterative method is based on matrix multiplication. An iterative method that is based on matrix vector multiplication will address all the drawbacks of direct methods. So there are, I can go ahead. There are two different types of iterative methods, and today we're going to be discussing the first type, and those are stationary iterative methods. So we're not going to get to, and the other type is non-stationary iterative methods, but we're not going to get to non-stationary iterative method until next week. So either type of method takes an initial guess. Often chosen to be the zero vector. And it computes a sequence of iterates, so we get x1, x2. That are hopefully converging to the solution x. So a stationary, hopefully they're converging to the exact solution x, and that's why we took a look at the convergence of one vector to another, dealing with the eigenvalues. So a stationary method has this form. Xk plus 1 equals g of xk. For some function g, so the solution x is a fixed point or a stationary point. So you've seen fixed point iteration already in solving nonlinear equations, right?
Yeah, previous class.
Right.
So this is a fixed point of G.
Right. So yes, x is going to be a fixed point of G, and so this is used to obtain the solution. All right. First of all, before we get into specific stationary iterative methods, we'll talk about what properties a stationary iterative method has in general. So we need to construct our G. And to construct, I'll just lay it down here. So to construct the suitable function G for these methods, we can use a splitting of the matrix. So we have A equals M minus N, where M is non-singular. Okay, so if we have AX equals B is our system that we're trying to solve, then we can substitute M minus N in the place of A. So we have M minus N times X equals B. So that gives MX minus NX equals B. And then, so we have MX equals NX plus B. So finally we get X equals M inverse NX plus B. So this is what we call, this is what our function G is. So G is a function of X is M inverse N X plus B. So now the iteration takes this form. So to get our next iterate, we have mxk plus 1 equals nx k plus b. And so that's how we go from one iterate to the next in these stationary iterative methods. And for the sake of efficiency, the splitting A equals M minus N, it should be chosen so that My equals C is easily solved, because we're going to be solving a system where we have to invert M, right? We have M times this vector right here is going to give us our solution. Okay, and so we can take a look at the convergence analysis of this also.
So you wrote x equals and gx equals the same thing, so the x
Right.
equals g of x in this case.
Well, g of x is a function of x, so we were looking for this this function right here. For x is actually our fixed point.
Okay.
Okay. So let's take a look at the convergence. So if we use the fact that x is the exact solution, so x is our exact solution, what we want to do is take a look at the convergence and what are any criteria. So have AX equals B, or actually what I just went through right here. So that gives us our exact. And then I'm going to subtract this from this line right here. Yeah, so that's going to be mx to the k plus 1 equals nx to the k plus b minus mx nx plus b. Okay, so when I subtract all of this, I'm going to get this, let's see, minus this. So we'll have m x to the k plus 1 minus x is equal to n x to the k minus x. And then we'll have plus b and minus b from there. So when I simplify this, my b's cancel. So keep in mind that this is with the exact solution. And then I'm going to invert m, move it to the other side. So I have x k plus 1 minus x equal to m inverse n of xk minus x. So now when we look at this, when we looked at like matrix vector multiplication before, we saw, I think, this was a while back, but when you have a matrix multiplied by like a vector xk, we can get this from it. So now we have m inverse n to the k, and we're going to have x to the x0 minus the exact solution x. So from this right here, we can see that after each iteration, the error after each iteration was obtained by multiplying the error from the previous iteration by this matrix right here, m inverse n. So therefore, for the error to converge to the 0 vector, the initial choice of x0, then we must have row of t less than 1. So the spectral radius must be less than 1, which is what we talked about last time. So now I think we're ready to go ahead and get into the different types of stationary iterative methods. And there's 3 different types that we're going to talk about today. And the first one is called the Jacobi method. Alright, so with the Jacobi method, the first thing that we'll do is, for convenience, we'll say A is equal to D plus L plus U, where D is the diagonal matrix, L is strictly, okay, so D, so here we would have AII equal to the diagonals and everything else is 0. L is strictly lower triangular. Where the elements of Lij are equal to Aij, where I is greater than j, and 0 if I is less than or equal to j. And then, of course, U is strictly upper triangular. So Uij is equal to Aij, where I is less than j, and it's 0 anywhere else. Okay, so now that we've defined D, L, and U, we can talk about the specific splitting that we use in the Jacobi method. So in all of these methods, we have the splitting A equals M minus N, but we define M and N differently for different methods. So here, for the Jacobi method, M is equal to D, and then N is equal to minus L plus U. So now when we plug this in to our iteration, we'll actually get the Jacobi method. So we have xk plus 1 equal to d inverse minus L plus U times xk plus b. So this is our iteration for the Jacobi matrix and for the Jacobi method. And we can also look at this in element by element form instead of just in matrix form. And that's what we'll do now. Alright, so if we take this right here, the last thing that I wrote, and so we write each row of this vector equation individually, we're going to get xi k plus 1 is equal to 1 over aii, that is each row. And so 1 over aii comes from the inverse, because if we invert a diagonal matrix, then it's just going to be 1 over each of those elements. So we get 1 over aii, and then bi minus the sum. So then we're going to have this matrix vector product to represent right here. So this matrix vector product, which is the last line on the previous board for the viewers at home, is just L and U. So we're not including the diagonal part. So the sum is going to be J not equal to I, but we're including the upper and lower triangular part since it's L plus U. Aij xk. So this description of the Jacobi method is helpful for its practical implementation, but it also reveals how the method can be improved. So if we have a component xk plus 1, or if we have the components xk plus 1 are computed in order, then the computation of this xk plus, or xi k plus 1 uses the components 1, 2, all the way up to I minus 1 of xk, even though those components have already been computed. So the order doesn't matter in which we compute these components, but we're using them when they've already been computed. So Gauss Seidel is the next one that we're going to discuss, and that kind of addresses this, the drawbacks from the Jacobi method. So by modifying the Jacobi method, Gauss Seidel actually uses the most up-to-date information available. So for Gauss Seidel, if we start with this here, with 1 over aii, minus. So we take this and we split it into two different sums. One's for the lower triangular part and one's for the upper triangular part. So we have j less than I of aij j to the k plus 1 minus j greater than I aij xj to the k. Okay, so now these are xk plus 1 because at this point they've already been computed. So that's why we want to split it up into the lower and upper triangular portions here. So now what we can do is go ahead and get everything with xk plus 1 on the left-hand side and multiply through by aii to eliminate this denominator out front. So I'll go ahead and do that. And when we do that, let's see, we're going to move this term over to this side. And when we move, well, I'll go ahead and do this first. So we've got j less than I of aij xj k plus 1 plus, now this was already multiplied by aii, or 1 over aii, so when I go through and I multiply both sides by aii, then it's just going to cancel it out. But this term has to be multiplied by it. And then on the right-hand side, what we have left is this aii will cancel out for anything inside the parentheses now. So we've got bi minus this last term here. J greater than I of aij xk. Now over here, this is I greater than j, so this is the lower triangular portion, and this is the diagonal part. So we can go ahead and just have it together all in one sum. So if I have it, I can just say j is less than or equal to I, so that's going to include the diagonal portion now. So aij xj to k plus 1 bi j less than I aij xj. Okay. Okay, so now this actually let's see, is going to lead us to the form of Gauss-Seidel, where we can see which matrix is a diagonal lower and upper triangular portion. So, but we can get it directly from this. So we know that this right here is the diagonal portion plus the lower triangular portion, and then this is minus u. So this is multiplied by xk plus 1, and this is multiplied by xk. So now we can write this as d plus L times xk plus 1 is equal to d minus u times xk. And if we want to, actually go ahead and solve for xk plus 1, then I just go ahead and invert this matrix and multiply on the left-hand side. So d plus L inverse times d minus u xk. And this is actually our Gauss-Seidel iteration. And this matrix right here is what we call our iteration matrix. Or actually, I'm sorry, this is M inverse, but M inverse N is what we would call our iteration matrix. So this is our iteration for Gauss-Seidel. So typically this iteration converges more rapidly than the Jacobi method, but the Jacobi method still has one significant advantage. Since the components of xk plus 1 are computed independently than all of the others, then Jacobi method, you can compute all of these components in parallel if you have the capabilities of doing that. But Gauss Seidel, you cannot. Each computation of xk plus 1 depends on the previous one for j less than I. So there's some drawbacks and advantages to each method. Now, there's another method, and it's called successive over relaxation, or SOR. So both of these previous iterations are guaranteed to converge if A is strictly diagonally dominant. So and that means if I have the absolute value of any diagonal element has to be greater than the sum of all the other entries, or the sum of the absolute value of all the other entries in the row for each row. So that's one way that we can guarantee convergence for both of these methods. Another way is guaranteed to converge is if A is symmetric positive definite. And I don't know if I've introduced this SPD, but we call those matrices SPD. Okay. So, however, in certain applications, both methods can converge quite slowly. So now with SOR, what we want to do is we just want to accelerate convergence. So first of all, we're going to rewrite Gauss-Seidel in a way that is not really helpful when you're trying to compute a solution, but it will be helpful to derive our SOR method. So we rewrite Gauss-Seidel this way. So xk plus 1 equal to xk times xk plus 1 minus xk. So here in the brackets is the step taken from xk to get to xk plus 1. So we have our previous solution times our step to get from xk to xk plus 1. However, the direction of this step corresponds, so the direction of this step corresponds closely to the step x. X minus xk. It may be possible to accelerate the convergence by increasing the length of this step right here. So if this step corresponds closely to this step. So when I say that we want to accelerate convergence by increasing the length of this step, what we want to do is essentially introduce a parameter. So So now we have x k plus 1 equal to xk plus omega times xk plus 1. So this comes from Gauss Seidel times xk. So this omega right here is going to allow us to increase the length of this step so that we get faster convergence. So by choosing omega greater than 1, then it's over relaxation. So that means we just go further along in that direction, closer to our solution. We're taking a larger step in the direction than Gauss-Seidel would normally call for. So we're just using omega to take a longer step, or to get closer to our solution faster. So let me go ahead and erase that first. So what we're going to look at now is just Gauss-Seidel, but now introducing this omega as well. So xi k plus 1 xi k plus omega times 1 over aii di, and then we still have our sums split, so j less than I, aij x j k plus 1 minus j greater than I, aij xjk, and then all minus xi to the k. So again, what we're going to do here is just go ahead and multiply through by aii and get all of our terms with xk plus 1 on the left-hand side. So if we go ahead and do that, we've got omega times this term right here, and also 1 over aii. So when we move it to the left-hand side, multiplying by aii, then we have omega j less than I, aij to the k plus 1, and then we'll have plus aii xi k plus 1, and then we get aii multiplied here times xi k, and then I'm gonna, so then what we have is omega times bi, and so when I multiply through by aii, all of 1 over aii is canceled out for everything that's in the parentheses, but it'll still affect this last term here. So this is the term we moved over, and then we have this sum aij xj to the k, and then we have aii xi k. So So all of that's still multiplied by omega. So now let's go ahead, or we're safe to go ahead and change, and instead of writing this in terms of matrix vector multiplication, just or on the element by element basis, we'll go ahead and write it as matrix vector multiplication. So this is omega times L plus, and this is just, omega times L, plus D, and all multiplied by xk plus 1. This right here is D xk plus omega B minus U xk minus dxk. Let me check and make sure. Yeah, everything looks right. Okay, so now I'm going to go ahead and distribute the omega throughout. And then over here. So now this is our SOR method. It looks slightly different from the note, so we can just rearrange by collecting all of the terms together and factoring things out. So that's what I'll go ahead and do now. So D plus omega L xk plus 1 is equal to, let's see, we want to collect all of our x terms together, and then factor out. So we'll get 1 minus omega times d minus omega u, and all of that was multiplied by xk, and then we have omega times b at the end. So this right here is our SOR iteration. And so, like I said before, and by introducing the parameter omega, it just helps us go further along in that search direction than Gauss-Seidel would have originally called for. Yes, that looks good. So now if W equals, if omega equals 1, then what would we have here?
0 and then to the non x's.
Right, so it actually reduces to the Gauss-Seidel. Right, so if we have 1, so this would be 0, so we just have minus omega x, but then we have d over here. So we have d inverse minus omega u, and then plus b. So SOR reduces to Gauss-Seidel when omega is equal to 1. So when omega is greater than 1, then that means we're going further along that search direction. So our iteration matrix for this, which is our n inverse n, and T is what we usually use to denote our iteration matrix. So it's just D plus omega L inverse times 1 minus omega D minus omega u. So that's just multiplying on the left-hand side by the inverse of that M matrix in the front. That gives us our iteration matrix n inverse n. So that's n inverse, and that's n right there. Does anybody have any questions about Anything so far? All right, so now, since both of these matrices, M and N are triangular, obviously, since we have D plus L, so that's the lower triangular portion, and here we have D and U, that's going to be the upper triangular portion. It follows that when I look at the determinant of this iteration matrix, it's just the product of the diagonal entries of each one. So we have the product of AII inverse times the product 1 minus omega AII, and that's equal to 1 minus omega to the n when we carry out this product. So because the determinant is the product of the eigenvalues, it follows that the spectral radius must be greater than or equal to this, or the absolute value of 1 minus omega. So from this, we can conclude that SOR converges only if we have that omega is between 0 and 2. So, and just from looking at this absolute value right here, we can see why that would happen, because that's what satisfies this inequality. Okay, so in some cases, it's even possible to determine the optimal value of omega for which the convergence would be the most rapid. And we'll take a look at an example like that now. And it's specifically for if A is a symmetric positive definite matrix. So if A is a symmetric positive definite matrix, N is tridiagonal. Then the optimal value for omega is this. So we get 2 over 1 plus the square root of 1 minus the spectral radius of t squared. So this is just an example of how to get the optimal value for a matrix that's SPD and tridiagonal. So where Tj is the iteration matrix, negative B inverse L plus U for the Jacobi method. So then, if the spectral radius of Tj is less than 1, then omega is going to be between 1 and 2. It's greater than or equal to 1, less than 2. So now a natural stopping criterion for any iterative method is to just check and see if your iterations are converging. So if we have xk minus xk plus 1 approaching is less than some tolerance. So that's how we would check to see if our iteration is converging. However, if we have the norm of t less than 1 in any natural matrix norms, so any of the induced matrix norms, then we have, I'm going to come over here for this, I think I can. So if we have that, then we've got the norm of xk minus x is less than or equal to the norm of t times the norm of xk minus 1 minus x, which is less than or equal to the norm of t times the norm of xk minus 1 minus xk plus the norm of t times the norm of xk minus x. So what we're looking at here is the error estimate, or checking to see this convergence. So this is going to yield the estimate xk, the norm of xk minus x is less than or equal to the norm of t over 1 minus the norm of t times the norm of xk minus xk minus 1. So that's kind of close together. All right. So from this right here, we can see the tolerance must be chosen with this in mind. The norm of t over 1 minus the norm of t. So from this right here. So if we're going to be comparing to see if this is less than some tolerance, then the tolerance must be chosen with this in mind right here, the norm of t. As this can be quite large when the norm of t is approximately 1. So when you're checking for convergence, you just want to take a look at the norm of t and keep this in mind when you're trying to set your tolerance that you're comparing this to. And so that's actually all for today. So yeah, we finished a little bit early again, but we'll be, I don't know if y'all heard this, but we will be in lab on Wednesday, and then next week we're going to get into non-stationary iterative methods, specifically the conjugate gradient method. So that's the method that the method of choice for these large sparse systems that we're talking about here. All right, so that's all for today.